Hello, this is Paul from Tech. In this video, let's prove Theorem 3.5.2, which is the properties of cross product. We do have a lot of important properties. Let's see one by one. So the first, we have a name. If we interchange, if we interchange the position of the two vectors, okay, the result will go to the opposite. This is not a commutative, right? So we have a name. We call it anticommutative. Okay, so it's different from dot product. We call anticommutative. And the second and third, of course, distributive, right? So that's distributive. So the first, we have to use the definition to prove it. Let me leave it here. The second, distributive, we also need to use the definition of the cross product. But the third, okay, so the right distributive, we can use A and B to prove. Okay, see, let me just put here. We can use A plus B. We can prove for C. I should later see why, because I can do a simple calculation U plus V cross W. Okay, by the first A, which equals inverse, right? You switch the order. Let me switch the order, which is a negative W cross U plus V. Okay, so this is A, right? And then distributor, okay, so we can use B. And then we can use B distributor, which is a negative W cross U. Another is also negative, okay? So negative W cross V, right? Okay. And we switch the order again. Therefore, switch the order, which is anticommutative. We use A again. What do we get? We get U cross W. So the first should be U cross W. The second, okay, so now go to the opposite. Is V cross W. Okay, definitely. This is the one, right? So it's the one for C. So C is correct. Okay, so C is easy. D, we have a name. Okay, so we call it homogeneity. The name is the same as the property is the same as dot product. Homogeneity. We have to use the definition of the product to cross product to prove. Let me leave here. E is super easy. Okay, so I'll just leave for you. Just use definition. I'll leave this for you. F, U cross U. You can use the definition. Oh, let me give you another proof. Okay, I can use A. Okay, see, I can use A. U cross U. I switch the order. Okay. See, what do we have? Switch the order, so therefore by A goes to the opposite of here U cross U, because U equals U is itself. Okay, this means what? This means the vector U cross U. Cross U the vector should be zero vector, because only zero vector equals the opposite of itself. So F is true, and E just leave yourself. So now let's prove A, B, and D. A is anticommutative, B is type of distributive, D is homogeneity. Okay, so now we verify the first by definition. Okay, anticommutative, which is a U cross V equals negative V cross U. What you can set up, so let's set up U is U1, U2, U3. Okay, the definition is in 3 space, and then V is V1, V2, and V3. So I can do calculation directly. See, therefore, U cross V by the definition. Okay. By the definition, what do we have? Is a vector. The first is U don't have a U1, don't have V1. Okay, that's it. U2, U3, V2, V3. Okay. Second is negative. Don't have a U2 and V2, which is a U1, U3, V1, V3. Okay, one more. Don't have V3, U3 and V3. So it's a U1, U2, V1, V2. See, that's the definition. And then we learn the determinant of matrix, right? You can see we can switch the order. Therefore, we get a negative. And the same, we switch the order of these 2 rows, switch the order. And therefore, we get a V go to the first, and the U go to the second. See, what do we have? We should go to the negative. So easy, we go to the negative of V2, V3, U2, U3. This is the property. Okay, so we learn switch to order is the property of row operations to the determinant. Okay, we learned before. Second type, so we go to negative. But therefore, this negative should be go to the negative, because the negative is outside. You see, there's a V1, V3, U1, U3. Okay, and then here is a switch the order V2, V1, V2, U1, U2. Okay, see, switch the order, row operation, we get a negative there. And then we look at the definition. So here is the cross product, right? So this is the cross product of V and U. Yeah, that's good. So anticommutative is easy to see. And then one more. B, distributive UV and W, distributive U. Okay, so, which is B. Let's verify B, U cross V plus W. We can distribute, right? We can distribute. Therefore, we have U cross V plus U cross W. Okay, see, distributive Y, distributive works. We have a UV set up, so we need to set up W, one more. Okay, so W, let me say W1, W2, and the W3. U1 to U2 is the same as before. We already set up. So therefore, I do calculation from the left. U cross V plus W. Okay, well this should be let me put a little bit. U is a U1, U2, U3, right? And the cross. What is a V plus W? Yeah, we know the addition. Just a V1 plus W1, V2 plus W2, V3 plus W3. This vector by the definition. So now we can look at the definition. Which is a vector. So the first, don't have the first which is a U2, U, get a little bit space, U3. And therefore is a V2 plus W2. Okay, don't have the first, so we have the second and the third. V3 plus W3. See that the first, the second is negative. don't have the second component, which is U1, U3, which is V1 plus W1, V3 plus W3. Okay, so, and then one more. The third component don't have the third, which is U1, U2, and then V1 plus W1, V2 plus W2. See the definition, right? This is the definition. And then we can break it down. Okay, so can we break it down? Okay. And we do have a property we learned before. Okay, we can break this down into the sum of two determinant, right? So we can break it down this term. See, break it down this, break it down this, break it down this. The same. That should be theorem. Let me give you the name 2.3.1. Okay, we check 2.3.1. We can break it down each into the sum of two vectors. So what is the first? The first is U2, U3, V2, V3, plus U2, U3, W2, W3. Okay, so that's the theorem 2.3.1. So we can break it down. Okay, so the same for other two terms. You can see this break it down. The negative U1, U3, V1, V3, V1, V3. Then plus the negative, which is a minus. So U1, U3. And then there's W1, W3. Okay, this is the second component. One more component, okay, which is positive, right? The last term should be this U1, U2, V1, V2, plus U1, U2, W1, W2. Yeah, is this okay? And therefore, we can use the sum of vectors. We change this into two vectors added together. See the first vector, after this term, and this term, and this term. What's that? That should be the cross product. Okay, so the first should, oh, let me just put it 2. So break it down. So therefore, now is U2, U3, V2, V3. The first component, second is negative. U1, U3, V1, V3. The third, which is U1, U2, V1, V2. Okay, so the first vector, okay, and then add the second vector, add this vector. Okay, see. I'm gonna put here a little bit. So get, yes. What do we have? Oops. So it's the plus, right? So it has a U2, U3. U2, U3, W2, W3, W2, W3, then negative again. So U1, U3, W1, W3, one more. The last is U1, U2, W1, W2. See, that's the sum of the two vectors. And then what do we have? And then the first is a cross product of U and V, right? So U vector plus V vector. That's the first. What is the second? The second is U cross W, right? By the definition, okay? By the definition again, which is U cross W. Now what do we get? See, Therefore, from the beginning, u cross v plus w, and then equals u cross v plus u cross w, which is the distributive, right? And that's all. Thank you. No, let me see. I think we missed a little. Oh yeah. So I missed one homogeneity. Okay, so let's prove D. Okay, one more last. The homogeneity, why we can take this out. One more. Sorry. D. So homogeneity. K times U cross V. Okay, so we can take the K out, which equals K times U cross V. Okay, that's the first. And the same also equals, let's look at it, is the first. Okay. And the second is U cross KV. Homogeneity, we can take the K out. So also equals K times U cross V. Okay, so the second, I think the second is easy. So we only need to verify the first part. See, so this 1 and 2. So we only need to verify the first. The second should be proved by the first, right? So I can show a little. You can see. Because this one equals, we switch. You can switch the order, which is 8, right? So anticommutative. By anticommutative, this should be KV cross U, but we need to put negative. And then by A, see? No, by the first of D. We can take the K outside, right? Therefore, there's what? There's a negative K. Or I say in this way. Take the K out, which is a K, right? Which is this. K times the negative, we can put it to anywhere. Okay, I put it to negative here. Negative V cross U. Of course, they are the same. And then we switch it again. Therefore, the negative will disappear. So that should be equals this one, exactly the same. So 2 is correct. Therefore, we only need to verify 1, the first. We use the definition. You can see why the first is correct. So now we check, verify 1. Okay. Why? Not difficult. So let me just put here. KU cross V equals what? KU, I know it's just K U1, right? K U2, K U3. So this is a KU, then cross V1, V2, V3. Okay, and then by the definition, this should be, let me put here, by the definition of cross product, this should be a vector. The first is KU2, KU3, V2, V3. Okay, the second is KU1, KU3, V1, V3, right? The third should be the first and the second. KU2, and then V1, V2. That's the definition, right? Okay, so now I'm looking. So we can factor, okay, so factor the K out. Can we? Okay, factor out k from the first row, right? Okay, the same for the second determinant and the same for the third. So we should have a k on each component, and then the k we can take out of the vector by the scalar multiplication. So you know we have this. We have a k outside, and then inside is u2, u3, v2, v3 negative, u1, u3, v1, v3, and then one more u1, u2, v1, v2. What's that? That's the cross product. Okay, that's the one we need. That's exactly k times u cross v. See, therefore we take the k outside the homogeneity, right? So we verify. Therefore, that's the proof for this theorem. Thank you.